All right, let's get started. All right, so just a few quick announcements before we get started, and then I have a video I'm going to show you. Doesn't really have much to do with computations, but well, I guess it does, just maybe to illustrate how important some of this stuff is. There's something that happened over the weekend in the Czech Republic I thought would be kind of interesting to show. All right, so real quick. The technical conference, I mentioned this last time, but your resumes, if you want your resumes included in the resume booklet that's going to be on the tables, you need to get that to Noah Morgan today because we're going to start printing all that stuff off tomorrow in preparation for the conference next week. Again, we're not going to have class during the conference, so you all should be free in the morning. So if you're interested in volunteering, contact Logan Stacks as soon as you can, and then he can get you a task to do. Maybe it'll, like I said, help you rub elbows, get some networking done that might lead to a potential internship or job down the line. I don't know if you all saw in your inbox, you all should have gotten an email from Don Rayburn in regards to a scholarship. Did everybody see that? Let me close this. What's that? Okay, I'll check with that. The West Virginia Society of Professional Engineers has a scholarship. Now we sent it out, some of the professors sent it out over the weekend, so maybe she didn't have a chance to send it out. She's probably, if she hasn't already sent it out, she'll send it out probably sometime early this morning. But the submission deadline for the scholarship is this Friday. So if you're interested, I would seek to get your application taken care of as soon as you can. And I guess on a more general note, just make sure that you're paying attention to the emails that you get from Dawn Rayburn. She's our administrative assistant within the Division of Engineering. And I know that sometimes your inbox feels like it's just getting full of a bunch of stuff. Well, I at least make sure you're sifting through it because some of that stuff could be some pretty important details. I mean, scholarships. I like money. I'm sure you do too. Before we also get fully into it, your homework one is due on Thursday. Now, we covered most of it last time. Does anybody have any questions at all? We still have the linear interpolation stuff to go through today. I think that's problem 6 and 7. So if you haven't done 6 and 7, no big deal. We'll cover that stuff today. But any of the other stuff, if you got any questions, I'd be more than happy to entertain them. Do you have a question? Oh. I thought you were raising. No, but the order of magnitude calculations don't seem right. Some of them are going to be a little off, and that's fine. Yeah, some of the order of magnitude calculations may be off. It just depends on what you're doing. So, any other questions? I mean, please, I want to make sure that. Yes, sir. You might as well put both, you know, what is actually being computed as well as your significant figures. And I know on some of them, it might be one significant figure, and that's fine. You know, it is what it is. So, any other questions? All right. Before we get into this, I just wanted to show you a video. This was trending on Facebook, or on YouTube. I think it started yesterday or something, but this was posted. A video out in the Czech Republic, and I just thought it was interesting. Fortunately, nobody died during this, so if that sort of sets the stage. But this is a game of what's called floorball. I'm guessing it's like an indoor hockey or something like that, and you'll kind of see what's going on here in a second. So this is in the Czech Republic, so I imagine the weather there is a little different than it is here. Next thing you know, everybody starts running, and you start to see why. Yeah, they had a lot of snow, so you can see the roof is failing. Ultimately, it's very similar to what happened to that failure out in Connecticut. The roof structure is very similar, but hopefully the cameraman did not stay there. They hopefully left the camera and ran. I don't know how they recovered the camera, but they did. Maybe it was a live stream or something of the game, and that's what we're looking at. But yeah, I just thought that was interesting. So so yeah, our computations matter because stuff like that can happen. All right. Okay. So if you haven't already done so, you can go ahead and log on to Blackboard. These notes should have posted. this is going to be some, I think, some more pretty basic stuff. Oh, a couple other one other announcement. If you haven't already gotten your calculator, your Casio, you're going to want to do that soon. We start officially using the Casio in class on Thursday, so we're actually going to go through some of the modes and operations and things like that. So if you haven't already gotten it, or at least gotten it ordered or something, I would get that taken care of as soon as you can. Okay. As far as I know, the bookstore stocks them, but I'm not 100% on that. But like I said, Amazon, Walmart, Target, you should be able to find one. All right, sound good? Okay, all right. So let's get actually into the topic of discussion for the day, which is we're continuing our discussion of fundamental calculations. And we really got two things I want to discuss today. The issue of linear interpolation, and then I want to go into some stuff regarding software and programming, some flowchart stuff and things like that. We're not going to directly use that stuff right now, but as we progress throughout the semester, we're going to be using things like Excel and MATLAB and what have you, and understanding some really basic stuff regarding programming will help you out, regardless of if you're an electrical engineer or civil engineer, mechanical engineer, or what have you. Understanding these processes helps out quite a bit. Okay, let's turn that on. Okay, so the first thing I want to talk about, though, is linear interpolation. Now, I imagine some of you have seen this before. Am I correct? How many of you have done this before, linear interpolation? Okay, so spattering of you. Okay, that's fine. Let me explain why this is important. So one of the things that we deal with in the world of engineering is sometimes we have phenomenon that are represented by really, really long equations. And it happens. It happens in the world of structural engineering, happens in the world of geotech and transportation, happens in mechanical engineering. I'm sure it happens in electrical engineering. And by and large, unless it's really, really important or really, really specific, we engineers are sometimes lazy and like to do the calculation as easy as possible. And whether we've got a really, really long equation or we're using real-world data, like we've gone out and we've collected data about a particular site or a particular system or what have you, and we need to perform some calculations, a lot of times that's going to involve looking values up in a table. I know I do this in my field quite a bit, and I know that every single one of you, regardless of whatever discipline of engineering you go into, is going to have to interpret data in a table in some fashion or another. And a lot of times what ends up happening is the data looks something like this. This is a really small table, but it can give you kind of an idea. So to give you a little bit of background, this particular table is listing what are called bearing capacity factors as a function of what's called the angle of internal friction. And without getting too deep into the world of civil engineering, the long and short of it is that these bearing capacity factors are used when you're designing shallow foundations. So, you know, in civil engineering we design structures. Those structures have to be supported by the ground, hence the use of a foundation. So I'm sure you all know what I mean when I say a foundation, you know, piles or footings or things like that. And based on some given soil properties, particularly the angle of internal friction, you can look up some different factors that you would use to ultimately size your foundation. Now, what ends up happening is you go to a table and you say, all right, I have an angle of internal friction of 2.3 degrees. So I went out to the site where I'm building this new office building or this new hospital or this new elementary school or what have you. And I went out and I collected some soil samples. I took those soil samples back to the lab, and I went and I did some tests to determine, you know, what's the cohesion of this soil, what's the angle of internal friction, and what have you. So I go through and I do all the lab testing, and I find that the lab testing tells me that for this particular soil, the angle of internal friction is, let's say, 2.3 degrees. I say, all right, so I've got an angle of 2.3 degrees, so the next thing I need to do is I need to determine some factors that I can use to ultimately size this foundation. So I go to this table and I say, well, I've got values for an angle of 2 degrees and I've got values for an angle of 3 degrees, but I don't have values listed for 2.3, right? So there's a couple of ways I can go about this. One way is I can actually break out the equations and go through and compute, well, what is it at 2.3 degrees? And that's fine, but by and large, that's usually not necessary in most cases of engineering specificity. In other words, if I linearly interpolate, or if I try and figure out well, what would the value be if I assumed a linear range between 2 and 3, and then I went and I computed it using the equations, by and large, there probably wouldn't be much difference anyways. So why don't I go ahead and use a simpler approach? And that's where linear interpolation comes into play. And it's pretty basic stuff. All I would do is I would say, okay, let's say I look up some values in a table. So I have a value here and a value here. And I want to determine, well, what's the value at a given point in between? Well, I just assume I have a linear relationship between these two. I'm sure you all know the equation of a line, y equals mx plus b. I have a feeling everybody's seen that before. So I just assume that I've got a line in between the two, and I ask myself, well, if I know the x value here, what's the y coordinate? And the nice thing about linear interpolation is it's a very plug-and-chug expression. It's literally plug and chug using the equation of a line. It's pretty powerful because I can use linear interpolation when I'm doing geotechnical engineering or structural engineering or environmental engineering or mechanical engineering. I can use that given principle for a variety of different data sets and for a variety of different goals, and it will still work. So it's a very powerful tool at an engineer's disposal for doing very basic computations. I'm going to show you an example here later of a more complex linear interpolation. And if you look at the comparison between what you get from linear interpolation and what you would get from using the actual equation, I mean, it's so minuscule it wouldn't really matter. So what I'm going to do is this. I'm going to go through a few basic examples of linear interpolation. Now, if you all look at the PDFs, I mean, you're going to see the answers right here. So, I mean, you're more than welcome to go along with the answer if you'd like. But I do want to at least walk you through not only how you would look up the appropriate values and how you would do the computations, but I might also break out our emulator that we use for the Casio just to show you maybe how you would input these values in the calculator we're going to use throughout the semester. Keep in mind, this isn't going to be a calculator tutorial, but maybe it's at least introducing you to what's going on. All right, sound good? Okay, so I've got here a table that's based on an angle of internal friction. I'm looking at 3 different bearing capacity factors, so an N sub C, an N sub Q, and an N sub gamma. That Y-looking thing is a lowercase gamma. It honestly doesn't really matter what the names are. The data could really be anything. Linear interpolation would still be done in the same fashion. So what I want to know is this. What is the value of N sub C if the angle is 2.3 degrees? Okay? So what I'm going to do is this. Let's see if my little pen is going to work today. So I'm looking at an angle of 2.3 degrees. So I'm going to be somewhere between here and here. Would everybody agree with that? So if I'm assuming a linear relationship between these two values, it's going to be somewhere between 6.3, I can do a little better than that, 6.3 and 6.62. Sound reasonable? Now before we do any calculations at all, anything whatsoever, let's just make a guess. Before we do any calculations, if the angle is 2.3 degrees, it's going to be somewhere between 6.3 and 6.62. Somebody just spit out a guess as to what you think this value ought to be, somewhere around. 6.3 to 6.4, something like that, right? How does 6.4 sound? Does that sound good? So before we do anything, let's just make a guess. And let's say that it's about 6.4. Nothing magical about that, just made a guess. All right? What I'm then going to do is I'm going to go through and do the computations, and let's see if we actually get this. All right? Now, going off of the relationship, in the previous slide, so here's my equation. It's dependent upon 2 things. It's dependent on the outside bound, so this, x and y sub 0 and x sub y sub 1. In other words, those are the 2 points that we know, and we need to know what's going on in the middle. So I'll walk you through this one, and then I think the next one I might let you all walk me through. All right. Oh, good. Dropped my pen. Oh, it got tangled. All right. So based on this table, I've got a few data points that I'm going to know. So I'm going to know x sub 0 and x sub 1. We're going to say that those are the 2 degrees and the 3 degrees. Okay? So the value in between is going to be x equals 2.3 degrees. All right? Now, the y values are going to be the n sub c. So the y value is going to be 6.3, and y sub 1 is going to be 6.62. Can everybody read that? Okay, all right. And what we want to know is the y value in between. So if I wanted to maybe draw a little picture as to what's going on, so this is the x-axis and this is the y-axis. So I've got a point somewhere about right here and a point somewhere about right here. This is an x value of 2. That's an x value of 3. This is a y value of what, 6.3. This is a y value of 6.62. So we're assuming in between these 2 points we've got a line that looks something about like that. Okay? And what I'm trying to figure out is this. I have an x value that's 2.3, and I want to know what's going on there. Does that make sense? Sound good? All right. Now, the equation that we use is pretty straightforward. Is there a way I can, maybe I can move this? There we go. Get that out of the way. Okay. So the equation that we use is pretty straightforward. So it's y equals y naught plus y1 minus y0 over x1 minus x0 times x minus x0. If you're wondering, you know, like, how does this relate to the equation of a line? If you look at this big fraction here, what do you have? You've got essentially the change in y over the change in x. So this big fraction right here is nothing more than the slope. Does that make sense? Okay. All right. So let's plug and chug. Let me turn my phone down. Goodness. Sorry about that. Okay. So y sub naught, that's going to be 6.3 plus, I got a big fraction, 6.62 minus 6.30 divided by, what, 3 minus 2? Is that right? And then 2.3 minus 2.0. All right. Anybody got any questions so far? Okay. Now that I've got the computation set up, now it's time to break out the calculator. Now I have here a little calculator emulator. So the idea is if I go through and I enter in some numbers, so for instance if I enter in 63, you can kind of see it. Everybody read that? All right. So I want to go through and enter this computation in. What happened with the screen there? Where did all those lines come from? Oh well. I don't know what happened there, but luckily I've got it written down right here. Okay, so I'm going to go through and enter this computation in, and it'll maybe highlight one of the nifty parts about this calculator. So we'll do 6.3 plus, and then I'm adding a fraction, right? Well, a couple things. First off, see how that fraction is enclosed in parentheses? So I can go ahead and put some parentheses in right there. I can use the arrow key to go back. Now inside right here I need a fraction, right? See this little button right here? It's under Calc, C-A-L-C. See that? Bam, now I have a fraction. So I can go through and I can start typing in values. So I could say 6.62 minus 6.3, right? I can use the arrow key and go down. Now you can see the cursor kind of flashing right here on the denominator, and I can do 3 minus 2. So you can actually enter in the equation, and it will literally appear as it should on your paper. All right? It's one of the nice things about this calculator is the input methods, you can kind of see the way it looks. All right, so I'm going to go, I use the arrow key on the right to go outside, multiplied by, what was that, 2.3 minus 2. Close it up, and then hit equals. Now, another nice thing about the calculator is it automatically spits out values in fractions if it can. But if you look above where it says delete, see where this says this S and D? Everybody see this key right here? S and D. That'll convert from different number formats, and if you hit that, you can see it spits that back out as a decimal. So the calculator spit out 6.396. So I'm curious, did anybody go along and do that with me on the calculator, and did anybody else get that? Everybody okay with that? Okay, good. All right, so if I go back here, I don't know what happened with these. I don't know what those are, but they're going away. What's that? The decimal point? Oh, yeah, it is all the decimal points. That's interesting. Well, most of them, at least. I don't know what happened there. That's going to bug me if I don't fix that. All right, I'm not redrawing that, though. I'm lazy. All right, so that came out to be 6.396. So first off, from a computational standpoint, the first thing you want to do is say, you know, that's your answer. You can do something like ANS or ANSWER. Either one's fine. But whenever you're doing a computation, you want to clearly identify that's the answer. Okay, now that's point one. Second off, does that answer make sense? Before we even move on, does that answer make sense? Okay, why are you saying that? Close to our projected value. Okay, there you go. So we guessed that the answer should be around, what, 6.39, 6.4. That's about what we got, right? That is a very critical tool in performing these computations. The idea that when you go through and do the computations, does the answer make sense? This is a pretty basic example. You know, we all could sort of look at the table and say, it should be around 6.4, and then we calculated and it was around 6.4. If we got 98.3 as our answer, we did something wrong, right? Make sense? There's a very good reason for doing stuff like that, for doing, you know, what we call the sanity check, just making sure that your values make sense. Because again, the stuff that we compute, it matters. I mean, we're talking about, you know, people's lives. Everybody good with this? Okay, so you all have all the calculations here, so you can go along with that. Sound good? All right. Now here's the another one. We'll do this one together, and well, in other words, I'm gonna have you all tell me what to write, and we'll see what we get. Okay. So now we're going to look up the value of n sub q if the angle is 3.7 degrees. So we need to be interpolating between which values? Last time we did between 2 and 3. What are we doing here? 3 and 4. So 3 and 4. 3 and 4. And which one's the n sub q, right? So this one and that one, right? Okay. Now, before we do anything, I want to make a guess. Somebody make a guess. Now keep in mind, the value is 3.7, okay? So it's a little closer to the 4 end than it is to the 3 end. So somebody just guess something. 1.45. We got a 1.45. Okay. That sounds good. I'll go with it. Okay. Like I said, you all have the answer, but I do want to go through this this calculation with you. All right. Sound good? So we've got, let's see, what do we have? We're going to need x sub 0 and x sub 1. And which ones are those? The 3 and the 4. So we'll say 3 and 4 degrees. And x is 3.7 degrees. So the y sub 0 and the y sub 1 are the 1.35 and the 1.49, right? And so y is what we're after. Sound good? All right. So we can go through and do that computation. There we go. All right. So we can go through and use the pen. Oop, my monitor tilted on me. Y equals, what do we got? Y sub 0 plus a quantity, y1 minus y0 divided by x1 minus x0 times that, right? So you tell me what to write. Y sub 0, what do we got? Get you all, there we go, 1.35. Get you all participating, plus what we got up top. And then on the bottom, 4 minus 3. Then we got all right. So if you've got a calculator, why don't you go ahead and go through and do this, and let's see what you get. First one that's got an answer. Like I said, I know you can look at it on the slide, but you know. 1.448. So pretty close to our guess, right? All right. Is anybody having any issues entering that in? Everybody good? All right. I'm going to go ahead and move on if anybody's got any questions. Again, you've got everything here so you can go along with the calculations if you need. Sound good? Okay. So, like I said, it's a pretty fundamental skill. I'm going to go through one that I think is a little more intricate. This is another extension of linear interpolation, but this one's a little more involved. This was called bilinear interpolation. So to give you kind of an idea, if we go back to this table, we really only have one variable changing. In other words, as the angle changes, we look up a value. So if, you know, phi equals 0, here's a value. If phi equals 2, here's a value, etc. Right? Sound good? On this table, this one's a little more complicated because now we've got two variables changing, because now we've got the angle changing, but we've also got this new variable changing alpha. So, you know, for a given angle and for a given alpha, we now have a value that we look at. So this table's a little more complicated. Our linear interpolation that we have to do is a little more intricate. Instead of performing linear interpolation, what we're really going to have to do is what's called bilinear interpolation. So the idea is this. I might give you an angle of, let's say, 30.7 degrees and an alpha of 6.3 degrees. Now what's the value? Well, we're going to have to interpolate not only, you know, up and down, but we're going to also have to interpolate left and right. The idea is this, you know, if you've got, you know, if we're looking at linear interpolation, we have a value here and a value here, and we're just trying to find a value in between. But bilinearly, we've got more going on. We've got, you know, two values on either end that we're linearly interpolating to find, you know, what are these, I guess, purple points right here, and then we've got to interpolate between those to find the real answer. So this one can be a little more involved, but it does happen. The constants that we're interpolating in this table are actually, they're another geotechnical set of constants. These are what are called active earth pressure coefficients, these K sub A's. That's what all these values in these tables are, K sub A. So like right here, this would be K sub A is 0.3138 or what have you. But the long and short of it is these earth pressure coefficients are used to determine the pressure on retaining walls. So if you're curious as to where these values come from. Okay, so what we're going to do is a linear interpolation with this, and I'm going to, instead of using the pen, I'm going to just sort of rely on the slides and walk us through this step by step, but I am going to circle the appropriate ones. So if we're determining the value for a K of 30.7 and 6.3, we're probably somewhere in, what is it, this range? Somewhere like that. Because here we've got, you know, a phi of 30 and a phi of 31, and here we've got, you know, an alpha of 6 and an alpha of 7. So it's going to be somewhere in between those four values, right? If you want to think of it like this, you can think of that those four values are essentially like this point here, this point here, this point here, and this point here. And our goal is to figure out where's that, right? Sound good? Okay. Now let me show you how this works, and we'll sort of take our time and walk through this. So when you perform linear interpolation in two directions like we're doing, the basic idea is to first interpolate in one direction and then interpolate in the other. So the first thing that we're going to do is we're going to interpolate up and down. So we're going to have to do that twice. The first thing that we're going to do is we're going to consider, okay, let's say that that angle is 30 degrees. Okay, if that angle is 30 degrees and our alpha is 6.3, that means we're going to have to interpolate between this and this. Okay, does that make sense? Okay, so let's just say the angle is 30. Okay, so we'll keep that as constant. So if alpha is 6.3, here's the alpha for 6, here's the alpha for 7. So we're probably going to be a little bit closer to this value than we are to this one, but in the end the range is pretty small. We go through, we plug and chug, so here's x sub 0, here's x sub 1, here's y sub 0, here's y sub 1. There's our value of x, and we need to calculate our value of y. If you go through and calculate that out, you'll get 0.3395. So, sound reasonable? Is that a pretty reasonable value to go off of? Okay. Now that's for alpha, or that's for phi equals 30 degrees. We then do the same thing for 31 degrees. So the same alpha values, but we then interpolate for 31 degrees. So we're using this value for Ka and this value for Ka. So this is y0 and this is y1. Go through and do the computation all over again, and we get 32.59. All right? Sound good? So the idea was, going back to my little picture here, those two interpolations were really trying to do this and this, to try and interpolate along this direction and interpolate along this direction. Now we need to take those two answers and interpolate this way. So we have an answer for an angle of 30 degrees, and we have an answer for an angle of 31 degrees. Well, our actual angle is 30.7. So we do it one more time, go through and interpolate, and we get an answer. Numerically, it comes out to 0.3300, and I'm carrying everything to 4 decimal places because that's what everything was in the table. Sound good? Now, if you actually saw the equation that is used to compute K sub A, it's kind of long. Okay, it's kind of involved. But to give you kind of an idea of the accuracy, if you actually use that equation, you get an answer of 0.3299. Pretty close, right? So linear interpolation works pretty well. All right. Anybody have any questions? Because that's basically what's going on in the last two problems on your homework. So I did want to go through that. Sound good? All right. I have one other general topic that I want to talk about, and that's a little bit about software and programming, and a little bit about flowcharts. We'll sort of, I guess, revisit this stuff as the semester progresses. We'll sort of keep bouncing back to this idea of software and programming, but this is some pretty important stuff. You know, you'll find when you get out of here that software is used quite a bit in our discipline. And there's nothing wrong with that. I don't have a problem with that. You know, the general purpose of some of these computational tools, and there's stuff for all sorts of different disciplines. So, for instance, I'm a structural engineer, so some of the things I use are things like STAD, that'll do a lot of complex structural analysis for you very quickly, or some things like finite elements, which is used across the board for civils, mechanicals, you name it. The purpose of a lot of these computational tools is to do a lot of rote grunt work calculations for you very quickly. And there's you know, nothing wrong with that. I think that's great, you know. without some of these, computational tools, some of the stuff that we do as engineers wouldn't be possible. So, that's great. The big thing, though, is making sure you understand what they're being used for and how they work. Yes, sir?
At my job, I use HEC-RAS a bunch.
For hydraulic modeling? So what you're doing is taking watersheds and determining what's the flow on a given channel and whether or not,
And I just plug in values, and then, let it run, and then I look at a certain point, and I can see, like, how much water is internal, or
Yeah.
the stage flow is.
And yeah, that's how we size things like culverts. That's how we determine whether or not there's enough room under the bridge to allow a given amount of water to pass. It's a very powerful tool. The danger, though, and your bosses or whoever you work with will tell you the same thing, is, a program like HEC-RAS will only get you so far. It only works well if the input going into it is accurate. And if you know how to operate the program appropriately. I mean, how many of you have heard the term garbage in, garbage out? You ever heard that? Well, it's a very common phrase among engineers and computer scientists that, a lot of these computational tools that we use are only as powerful as the users using them. If I took a structural analysis tool like STAD and I, modeled, let's say the new building, the new Weisberg building. And I put all the beams and columns everywhere, but all my dimensions were wrong. The beam lengths were wrong and the story heights were wrong. Well, the analysis would be wrong. Okay, so making sure that stuff is modeled appropriately really matters. And also, there's something to be said about understanding how those programs work. For instance, I teach structural analysis here, and near the end of the semester, we go into things like matrix analysis and how programs like STAD run. Now, don't get me wrong, I'm not expecting the students to write a full-blown program that will do everything that STAD can do for a given homework assignment. And oh, by the way, you have a week to do it. No, I'm not doing that. But I do want you to understand the basic principles as to how they run. Because if you understand that, you'll be better equipped to not only troubleshoot the programs when something goes wrong, but you'll also have a good understanding as to whether or not the answers you're getting make sense. I mean, you mentioned HEC-RAS. The more you use HEC-RAS and the more experience you have with it, the better you will become at things like, you're doing a given flow analysis and you get a capacity that doesn't make any sense. You'll be able to run that program, but that isn't right. So there's some input wrong or some setting wrong that something's up with that calculation. There's so many times that and it's a little scary at times that I've gone through and looked at calculations and checked programs, and somebody will say, well, that's what the program said. I hit the little button and it spit out these numbers, and that's what I'm going with. No, you need to go through and check that. So, I mean, and plus, keep in mind, programs are written by human beings, and human beings can make mistakes. I mentioned that Call of Duty analogy at the very beginning. If you haven't played Call of Duty for 2 or 3 weeks and you turn your PS4 on, what's the first thing it does? It starts uploading or downloading patches and software updates because there was stuff wrong with it, and now they got to fix it. So that stuff happens in engineering too. Couple things I will mention. There are so many different programming languages out there that any one of them could probably be used to produce some of the software that we need. Some software packages are better than others, especially for what we do. For instance, like I mentioned with structural analysis, a lot of the computations that are involved in structural analysis are matrix calculations. So a program like MATLAB works very well for that type of analysis because that's what MATLAB was written for, was matrix math. And we'll explore MATLAB as the semester goes on. Basic might be a little easier for some graphic user interfaces or things like that. Fortran's also a very more classic but very popular engineering programming language. There's a lot of different languages out there. They all have their advantages and disadvantages. But I want to at least give you a general idea behind how a software program works. And it doesn't matter what language you're using or what you're after. Our programs in our world tend to follow a general pattern that looks something like this. So let's say, like I said, I apologize for bringing all the structure stuff into the room, but I'm a structural engineer, and that's what I reference a lot of my stuff off of. Let's say that I'm trying to do a beam analysis. So the first thing I'm going to have to do is input some data. You know, how long is the beam? How much force am I putting on the beam? Is the beam made out of steel? Is it made out of concrete? Is it made out of copper? Is it made out of plastic? How deep is it, et cetera? I need to input all of those variables that matter. Next thing that will happen is either a series of computations or a series of decision-making processes. You know, is the beam simply supported? Is it fixed? If it is fixed, do this. If not, do that. You know, there has to be some decision process going on. Maybe the decision process is just to carry the calculations and print it out. That might be fine too. We'll get into what that means here in a second. Obviously, in our world, we're going to have some computations that need to be performed. So sometimes those computations are performed over and over again. It just depends on what we're doing. And then next, output. We want the output spit out in a fashion that we understand. A table of computer garbage really doesn't help me, but a nice graph of the deflection of the beam as the load's being put on, well, that might help me out a little more. Usually, when you're trying to write a program, and this is true not just for writing a computer program, but performing an engineering task across the board, a lot of times you'll find that the very first step is to create some sort of flow chart. Start off defining the requirements and the constraints, create some preliminary design. You notice here there's this diamond-shaped task. Is the solution feasible? If it is, keep going. If not, loop back around. You can kind of get an idea of what's going on. And then ultimately, if you're trying to write a computer program, you can take that flow chart and then extend it into maybe writing some code and ultimately writing the program. A lot of times, I know students can see a bunch of flow charts and a bunch of these decision tools and go, oh my goodness, what is going on here? But ultimately, this stuff isn't that bad. Flow charting is really meant to make your life a little easier in terms of developing a program and developing a process for a system. And it's really great for if you're trying to write some program or you're trying to design some system and you're thinking, gosh, I kind of get the idea, but I really don't understand the programming language aspect. I don't understand the computational aspect. Well, maybe just literally drawing it out on a sheet of paper or something like that can help you formulate your thought patterns. These are some general symbols that go along with flow charts and whatnot. We're not going to get too invested into this. I do want to make a point, though, that arguably one of the ones that's most commonly used is this diamond-shaped decision point. Basically, going into that, we determine whether or not, for instance, our answer is yes or our answer is no. Let's consider this. So I put this up here as a little bit of a joke, but I honestly think that this is a really nice example to understand what's going on. How many of you have seen something like this before? I'm sure a lot of people have. So we're considering the following engineering flowchart, quote-unquote engineering flowchart. So pretty basic. Does it move? Okay, let's say yes, it does move. Should it move? Well, if the answer is yes, good, let it move. If the answer is, if it moves and in fact should not move, then we need to arrest that movement with the age-old construction material of duct tape, right? Now let's say it doesn't move. If it shouldn't move, great, no issue, right? If it doesn't move but it should, well, there's where WD-40 comes into play, right? Very classic, very basic stuff, right? Okay, now, this is just a pretty basic general understanding of what's going on. This is that same process using, I guess, flowchart symbology. So we'll start off our process. The first question we asked was, does it move? Okay? that would be a decision point, because we would then have to ascertain, does it move? Is the answer yes, or is the answer no? So from that decision point, we have two different options, okay? So question, does it move? Let's say yes, it does move. Should it move? There's another decision point. So within each given loop of, or flow through this program, we have two decisions that we have to make, regardless which direction we go. Does it move, and should it? So does it move? Yes. Should it move? Yes. No problem, and the program ends. Does it move? Yes. Should it move? No. Apply duct tape, and the program ends. Make sense? So notice how there's four potential paths for the program to end. So we have, one towards duct tape, one towards no problem, another towards no problem, and then another towards applying WD-40. Okay, does that make sense? Okay, so this would be outlining the problem using engineering terminology. We have the program start and the program end. We have decision points, and then we have action statements, either no problem or applying either duct tape or WD-40. Okay, now this would be that same program written in some form of a computer language. Now, honestly, a particular syntax, whether or not I'm using ifs or how I'm spacing stuff or how stuff's going on a particular line, that stuff doesn't really matter, because ultimately I would take this and say, well, how would I write this program in C#, or how would I write this program in Python or Java or MATLAB? But in the end, I think even looking at this from a programming aspect, this isn't that complicated. So think about it like this. All right, let's just start the program. Okay, let's consider an object that moves and in fact should move. Okay, so program starts. If the object moves equals yes, so our object in fact does move. If the object should move equals yes, take no action, that's it, and then we end our program. And that's basically it. Let's say it shouldn't move. If object moves equals yes. If the object should move equals yes, well, that's not the case. Then we skip down and we say apply duct tape. Everybody kind of following this? Okay. This particular type of program utilizes what's called a nested if statement. The idea is you have if statements inside of if statements. Does that make sense? But that might seem a little complicated, but again, going back to our flow chart, okay, every path along this flow chart required two decisions to be made, right? Every path requires two decisions, whether or not it moves and whether or not it should move. Same story here, right? Okay, does that make sense? Anybody have any questions about this? I just wanted you all to have a general understanding of this stuff. We're going to probably, hit this information up back and forth as the semester progresses. We'll do some programming things in Excel and some things in MATLAB, and we'll sort of return to this, but I wanted to give you all a general idea as of now. Everybody good so far? Okay. So here's what we're going to do, I guess, for the rest of the day. So you all have your homework assignment. As this loads up. Okay. Now here's the homework assignment. Again, it's due on Thursday. Last time we covered how to do problems 1 through 5. You all should be able to do problems 6 and 7 today, and then that's basically all the homework, all of the homework assignment. So what I'm going to do, I guess, is I'm going to shut up and let you all sort of work on your homework assignment if you would like. Again, you all are free to, if you want to work on it now, that's fine. If you want to go ahead and leave and grab some breakfast, that's fine too. But I'll be sticking around until 9:15. And with that, I'm going to let you all sort of do your work before that, though.
So you posted some examples of homework.
Yes.
And you want it formatted exactly like that. And second question is, can you have more than one problem or
That's a good question. So two parts. Let me take the second one first. So the second question was, can we have more than 2 problems on a page? For an assignment like this, yeah, that's fine. I'll say that when you get to a class like steel design or highway design or something like that, the problems just get so much longer that you really do need to start each problem on a new page so you understand what's going on. But I understand some of these questions are really like one line, and then you're like a whole nother sheet of paper, so I'm fine with that. As for the format, I would like you to follow that sample homework 1 as closely as possible. I understand that if you have notebook paper instead of quad paper, engineering paper, that's fine. Just do me a favor, none of the perforations on the ends, none of those. Okay. Beyond that, that's fine.
Like the page count at the top right,
Mm-hmm.
is that per problem or
Per the assignment. The idea is this: if I give a submission to a colleague or to an employer or something like that, and I know that whatever I give them should have 6 pages, I'm going to say 1 out of 6, 2 out of 6, 3 out of 6. So if something gets lost, or it's pretty easy to know which one got lost. So yeah, per assignment or per submission. Yes, sir. That's more than fine. Yes, that is what you're going to be using more often than not throughout engineering. So yeah. Yes, sir. That's a good point. You probably do need that. I'll be honest. I meant to wait a few minutes because of the wreck on I-64, and then I just completely forgot about it. So thank you. So sign-in sheets going around. It's somewhere over here. If you would like to leave, I'm not going to stop you. You can come up and sign that to indicate you were here, and then you all can go ahead and bounce. One more question. Yes, sir. Yes, that is correct.
Okay, so if you did that with one of these, if you were to round it before you changed it into years, or if you were to round it as you changed it into days, days per year, right, for 2017. This one, if you did order of magnitude, it'd be 1,000, and this would round to 1,000 as well. If you times it, it's like 70,000 something.
No, just round that one in order of magnitude.
So you don't, for the example, you had it like doing orders of magnitude before.
True, but think about it like this. At the beginning, we knew the original input. So for that, if you're talking about the age of West Virginia, you're only doing that calculation just to determine how many years West Virginia is. But you could look that up and just say West Virginia is 154 years old.
Right.
You see what I mean?
So we don't have to round for the order of magnitude before.
For that one, yeah. Yeah. Yes, sir.
I have a question.
Yeah.
How do you find the
Okay, all right, that's a good question. Well, I'll do this, okay? So this might help out everybody for problem number 5. I'm not going to carry it all the way through, but I'll give you kind of an idea, okay? First off, I'll say 2 things. So the numbers, like the 1/2, the constants being multiplied don't really matter, because think about it like this. If I have 6 feet and I take half of 6 feet, that's still 3 feet. So the numbers don't really change the units, but the exponents do. Now let me give you kind of an idea. I'll kind of walk you through the first one, but that's the only one I'm going to do. So if I look at, let's say, the first one, I have a force times a distance minus a distance, right? So on number 1, I have a force, so we'll say F x2 minus x1, right? On the left side of the equation. So that comes out to be, the force is in newtons, right? The distances are in meters, right? Make sense? So what is meters minus meters? In other words, think about it like this. If I have 4 meters and I take away 2 meters, what do I have? Still meters, right? So I'm going to have newtons times meters, right? So over here on the left side of this equation, I'm going to have Newton meters, right? What that means is over here, I better have Newton meters as well. Make sense? Some of them that may work out, and some of them it may not. Okay. So what you need to do is assess whether or not the units are compatible. So for instance, on number 2, on the left side is going to be what? Newtons, right? Because this is newtons times meters. This is just newtons. The question is, if this is newtons, is this expression here on the right, is it in newtons as well? Okay? Because in the realm of equality, if I have this term equals this term, it's got to be the same units. Okay? Did that help answer your question? So you're going to go through and carry all this out. Remember, that if you have a kilogram times a meters per second squared, that comes out to be a Newton, right? So I will go ahead and write that one out for you. So 1 kilogram times a meter per second squared is 1 Newton. If you haven't signed the sign-in sheet, make sure you do so. All right. Sound good? All right. I'm going to go ahead and pause the video and let you all keep on trucking.